We've analyzed the logistic equation using a phase line, but we can actually solve this equation exactly. So let's go ahead and do that. So this differential equation is separable. Every autonomous equation is separable because t doesn't show up anywhere, so we can always separate the variables. So let's do that separation. We're going to have to multiply both sides by dt and also divide both sides by p times 1 minus p over k. So when we do that, we get dp over p times 1 minus p over k equals r dt. Okay. Now remember, the next thing that we're going to do is integrate on both sides. The integral on the right is no problem, but the integral on the left, well, this integrand is actually a rational function of p. So to solve this calculate this integral, we're going to have to do partial fractions. So let's see, what's that going to look like? It's 1 over p times 1 minus p over k. So fortunately the denominator is already factored, so we're going to get something like a over p plus b over 1 minus p over k. And then we just have to figure out a and b. So we can, right there are some nice p values we can use. When we plug in, I guess first we need to clear the denominators. So we get 1 equals a times 1 minus p over k plus b times p. Now when we plug in p equals 0, we get 1 equals, the b term goes away, we just get a. So now we know a. And when p is k, we get 1 equals, now the a term goes away, and we get k times b. So that means b is 1 over k. Okay, so now we can take this equation that we were going to integrate and actually do the integral. So on the right-hand side, we had the integral of r times dt, and that's just rt plus a constant. On the left-hand side, we need to integrate a, which is 1, over p, plus b, which is 1 over k, over 1 minus p over k. And we're going to integrate dp. All right. So the integral of 1 over p with respect to p, that's natural log absolute value of p, plus this 1 over k we can move out in front. So now we need the integral of 1 minus p over k. And that's actually minus k times natural log absolute value 1 minus p over k. So if you aren't sure about this one, differentiate this to make sure, to double check that this is the correct antiderivative. When you differentiate this, the chain rule spits out a factor of minus 1 over k, which cancels this minus k here. So on the right-hand side, rt plus c. Now we can simplify a little bit. This is natural log absolute value of p minus, the k's simplify away, and we get natural log absolute value 1 minus p over k equals rt plus c. Now look, we have a difference of natural logs, so we can put these two natural logs together. We get natural log absolute value of p over 1 minus p over k equals rt plus c. Now we can exponentiate. On the left-hand side, we get absolute value of p over 1 minus p over k. On the right-hand side, we get e to the rt times e to the ct, but as usual, I'm going to let e to the c be a, so a like that. And we can remove the absolute values at the expense of putting a plus or minus on the right-hand side, but that just means a can be anything. So now we have p over 1 minus p over k equals a e to the rt. And remember, now we need to solve for p. So solving this sort of equation for p, it's algebraically it's a little annoying, but it's not difficult exactly. It's just kind of a lot of writing. So we'll clear the denominator here. We get on the left-hand side p, on the right-hand side ae to the rt minus a over k e to the rt times p. And then we can move this term on the right-hand side with p, move it to the left. So now we have p plus a over k e to the rt times p equals a e to the rt. Now we can factor out the p. P times 1 plus a over k e to the rt equals a e to the rt. Now we can divide. So our function p is a e to the rt over 1 plus a over k e to the rt. Okay. As kind of a finishing touch, people will often multiply the numerator and denominator by e to the minus rt. In fact, even k over a e to the minus rt. So do that in the numerator and the denominator. So then we get p equals, in the numerator, let's see, the a's simplify. The e to the rt times e to the minus rt is just 1, so we're left with k. In the denominator, right, these second pieces, those just multiply together to give us 1, and then k over a e to the minus rt times 1 is k over a e to the minus rt. Okay, so finally we got a solution to our logistic equation. To get a handle on what this actually looks like, what these solutions actually look like, let's graph an example. So K is our carrying capacity, so just to have an example, let's let that be 100. And A is actually related to our initial condition. It's not equal to our initial condition, but it's related to our initial condition. To figure out the relationship between A and the initial population, let's call the initial population P sub 0, and that's P of 0. But if we plug in 0 into this, we get K over 1 plus K over A e to the 0. So that's K over 1 plus K over A. Okay, and now we can solve for A. So let's see, take reciprocals on both sides, I guess. 1 over P sub 0 equals 1 plus K over A over K. Let's multiply both sides by K. K over P sub 0 equals 1 plus K over A. Subtract 1 from both sides. And remember, we're solving for A, so let's take reciprocals again. 1 over K over P sub 0 minus 1 equals A over K. And then multiply both sides by K. So we get A is actually let's stop right here, because that's actually K over A is the piece that shows up in this equation. So K over A is K over P naught minus 1. So we have our population is K over 1 plus, right, K over P naught minus 1 times e to the minus RT. Okay, so usually in practice, how we'll write this is we'll write k over 1 plus some constant times e to the minus rt. And then we'll just use an initial condition to find this constant. But, you know, if we really wanted to write this constant in terms of the initial condition, this is the formula that we get. So let's graph this thing to see what it looks like. So again, we are going to take for our carrying capacity 100. For our growth rate, let's make the growth rate pretty big just so that we don't have to wait too long to see things changing. So let's say our growth rate is 20%, which is pretty big. And for our initial population, let's say 10. So let's put this all into a graph. We're going to be graphing 100 over 1 plus, so k is 100 over p sub 0, that's 10 minus 1 is 9, so 9 e to the minus 0.2 t. So let's graph this. Okay, so I'm going to call it f of x in GeoGebra just because that's how we keep GeoGebra happy. So 100 divided by 1 plus 9 times e to the negative 0.2 times, and I'm going to use x instead of t because that's how we keep GeoGebra happy. Okay, graph that. So we can't see anything right now, but that's just because, right, remember our population starts at 10, so we'd better look at least up to 10. So there's 10. And if we zoom out a little bit more, you can see as time goes on, the population kind of levels off at 100, which makes perfect sense because remember 100 was our carrying capacity. So, this function that we wrote down actually is pretty convincing as a population model because, you know, when the population is small, it looks like exponential growth. But then as population reaches the carrying capacity, the population's growth slows down until it levels off near the carrying capacity. And this is exactly the sort of behavior we were looking for when we wrote down the logistic equation in the first place.